everybody. We'll get started. Can everyone hear me okay? Do we need the microphone? Does it sound okay? Good? Perfect. Okay, well, good morning, everyone. My name is Corey Osis. I'm an assistant professor in material science. And we're very excited to commence the data-driven materials modeling workshop. Thank you, everyone, for registering. I want to make sure that everyone has the name tag. If you don't have the name tag, please check in with Tia and Hal outside. This is a 3-day workshop. Okay, so each day we're going to have, we'll have more or less the same schedule. I'll go through that in a bit. But I just want to first introduce, because we're very fortunate to be able to have 3 very nice speakers, both experts in what they're going to be discussing and teaching. Today we have Dr. Olexander Isayev from Carnegie Mellon. He's right here. He's going to be the speaker today. Tomorrow we have John Keith from Pittsburgh, and then on Friday we have Eric Lugin from Northwestern. Okay? And they're going to be covering different topics, so make sure to stay tuned to what topics are being covered for each day. I want to acknowledge our very important sponsors. We have support from the IDIES Institute for Data Intensive Engineering and Science, from ROSEI, the Ralph O'Connor Sustainability Energy Institute, and then from ARCH, the Advanced Research Computing at Hopkins. I'm going to try to have this little QR code here. This QR code will connect you to our website, where you can find all of the links for the exercises. We'll update them each day. You'll have the updated schedule there. All the information should be accessible from the QR code. Okay? Otherwise, you can also go here and then go to the workshop tab. All right. So for the general schedule, this is the general workflow for the next 3 days. Okay. So we have the light breakfast starting at 9:15. I hope you're able to enjoy that. Then we start at 10 with the keynote speaker. At roughly 11 o'clock. We'll have an internal Hopkins faculty speak on the topic for the day and sort of introduce the workshop in the afternoon. We're going to have lunch at noon, very important. And then after lunch, we're going to have basically a session. It's going to be led by students and postdocs. So there's 2 things I want to mention. Oh, and then very importantly, at 3 p.m. we have snacks. By the way, there should be coffee outside all day. I drink a lot of coffee. I hope you do too. So it's available outside. Feel free to come in and out as you need. Few things. This is the first time we're organizing this event, and it's actually my first event. Okay, so we've had a lot of late people register, and we want to be as accommodating as possible. Regarding lunch, okay, so we have to plan all these things in advance. If for whatever reason, we should be okay today, but if for whatever reason we run out of lunches, okay, let one of us know. We're going to do our best to accommodate. But otherwise, we'll take you out to lunch. Okay, we figure it out. But we're organizing. We're figuring these things out. So the lunch just be forgiving with that. And lastly, with the workshop led by the students, this is also a very good opportunity for them. So for some of them, it's going to be the first time they're teaching. What this means is that I hope you engage with them. Okay, so make sure to ask questions. When I'm speaking, when the others, I'll let them decide for themselves. When I'm speaking, certainly feel free to interrupt. Okay, so we'll take questions. I want this to be an open format. We don't need to go through any to get to any point in the slides. My goal here is that you can pick up some of the information that we're interested in sharing with you today. Any questions? Nope? Okay. Just want to acknowledge the workshop organizers. We have Brandon Bukowski from ChemBE. He's over there. He'll be leading day 2. And then we have Tina Kirk, who's in materials with me. He's over there. He's leading day 3. Okay, so again, if there's any issues whatsoever, feel free to tag one of us and talk to us, and we'll work through it. Okay. All right. Well, we at Hopkins, we're always very interested in metrics. So if we could take 2 minutes, you can actually find this link from the workshop website. It's the pre-survey. It should take 2 minutes. We just want to get a sense of where you are computationally. We want to understand what your goals are for the workshop. If you could fill that out for us, we'd really appreciate it. It'll take 2 minutes to do that. Yeah.
Define competent coding.
Listen, this is subjective. So you just want to get a sense. I mean, if you are using coding every day, I would say that you're probably advanced, right? If you don't use it very often, maybe you pick one of the lower levels. That's the sense we want to get is how often are you coding? How comfortable do you feel with it? We want to see what stage you would rate yourself at. But it's subjective. You can put advanced for everything if you want. Black belt.
Yeah, I'm not gonna lie. I'm competent enough to Google.
All right, I think most people are done, right? Thumbs up? Set? Good, all right, perfect. Thank you for doing that. We appreciate the metrics, so we can improve for next time. All right, so the specific schedule for today, we have a real treat. The keynote seminar is by Dr. Isayev, who's here on the left. And then for the workshop, today is going to be led by the Entropy for Energy group, S4E, that's the website here. And they're going to be talking about how to navigate and perform high throughput density functional theory calculations, thermodynamic analysis, structural prototypes, modeling disordered materials, and a little bit of machine learning for property prediction. And I also want to give credit. A lot of these topics have been inspired, borrowed from the original AFLO school. And I give the link here. You can see that's been set up by the team there. They go into a lot more depth in some of these topics, and so if you have more interest, feel free to check them out. Just like this workshop, all the exercises are available, the presentations, so be sure to check that out. And now I'd like to introduce our keynote speaker, okay, Dr. Olexander Isayev, Oles. He's associate professor in chemistry at Carnegie Mellon University. He's a world leader in theoretical and computational chemistry, machine learning, cheminformatics, drug delivery, computational and molecular design, material informatics. He's won a number of awards, including Scilog Fellow and ACS Emerging Technology Award. He's actually someone that I've known for 10 years, we counted yesterday. He was my first collaborator as a PhD student. I was a PhD student, brand new, and he was a research scientist, and we were put on a project together. And I want to acknowledge and thank you for being such a wonderful mentor and for getting me into this beautiful subject area. And with that, we welcome Oles to give the talk.
Thank you for organizing this workshop.
So I'll stop sharing.
Great. Thank you, Corey. It's really a pleasure to be here and seeing so many faces. So the title of my talk is rather technical, but since this is an educational event, I'd like to start first, show you the motivation why machine learning have impact in computational quantum chemistry, and show you a little bit how machine learning potentials are made, and then later show you applications, essentially how ML potentials can be applied. I mostly work in organic molecules of matter and show you a little bit chemical reactions. And then you came for ML and material science, but also at the end of my talk, hopefully will make there, show you a little bit high throughput experiments and some of the robotic system we have at CMU. Okay, so before I run out of time, all of that is possible because of my wonderful team at CMU. This is us in front of the historic Mellon Institute. Funding by a number of agencies, National Science Foundation, Naval Research, and a bunch of other agencies. A lot of work done in collaboration, and also be a part of the new NSF-funded institute called Center for Computer-Assisted Synthesis. You might recognize some of the faces. It's a fun team of synthetic organic chemists, analytical chemists, computational chemists, and computer scientists who work together to kind of digitize organic synthesis and related things. Now, I'd like to ask, if you stop on the street and ask, can you imagine chemist? You will, in the imagination, I think us, at least me as a chemist, we have this problem of the image, right? So it's a strange people mixing liquids, maybe some fume hoods. Now, if you Google it for images, in image banks, it's people mixing colorful, bright liquids, right? It's always, shiny, bright liquids. But in reality, so this is modern chemistry. By the way, I also love metric. I will not force you to do QR code. How many of you hate chemistry in school? Because you will have to stick with me for an hour. So there's going to be some chemistry here. How many of you took machine learning class? Couple? Okay. Great. Now, but none of these images correctly describe me, because as a computational person, my lab kind of a messy desk. We do all our simulations on the computers. And I think the revolution what's happening right now can be attributed to these chips called GPUs, right? Some of you might game, so you use these chips. But they're very, very powerful to do linear algebra and crunching numbers, matrices, vectors, right? So Pittsburgh is a city of bridges, so Pittsburgh Supercomputing Center hosts a very nice machine called Bridges, which use GPUs, and we're one of the heavy users. And also, we have new algorithms, we have new hardware for computations, but we also have new hardware for experiment, and hopefully at the end, kind of close this loop to show you some of the experiment automation. Now, to get all of us on the same page, what is computational chemistry, right? So we use mathematical tools and computer programs to simulate processes related to chemistry problems. In particular, all molecules, materials are quantum, right? So we solve Schrödinger equation. You guys in material science use plane wave, some hybrid methods, right? For molecule, for us, we use typically, molecular orbitals, atomic orbitals. So we solve Schrödinger equation for molecular material system, right? And the definition of what is called ab initio quantum chemistry, if you don't include any empirical parameters, right, you solve from what's called first principles or without using any experiment. Now, what this is good for, right? It's actually very, very useful. It uses materials design, molecular design, drug discovery. So solving the Schrödinger equation allows you to predict, compute various types of spectroscopy, IR, mass spec, NMR. Right? Interaction of molecules, excitation, molecules plus light, and design of reaction, catalyst design. So all of that applications are done through methods of computational chemistry. Promise, this is the only slide with equation, right? this is your, the beautiful, simple h psi equal e psi, right? So this is our time-independent Schrodinger equation. Underneath our Hamiltonian operator, we have, kinetic and potential terms, right? So you have nuclear electron, electron, and different terms, right? And you cannot solve this analytically for anything practical. So, and therefore, we use various numeric approximations to solve this equation. One of the way how to do it is what's called the density functional theory, which you will talk about in the afternoon. But I think the fundamental principle here, right, our friend Born-Oppenheimer approximation, which separates nuclear and electronic degrees of freedom. So you treat motion of nuclei classically, hence the principle of molecular dynamics, and you treat only electronic degrees of freedom with your electronic Hamiltonian. Now, the long dilemma, because you have to solve Schrodinger equation numerically, is it's expensive. And therefore, we have the variety of different approximations. If you want to do realistic simulation, materials, grain boundaries, proteins, you have thousands, maybe millions of atoms. You cannot solve that, right? Hence, we have a variety of empirical force fields, or what's called the classical force fields, which imagine your molecular system as the system, essentially every atom is a ball, and every chemical bond is a spring. And therefore you have this harmonic approximation, have very simple analytical form of the bond term, angular and other terms. Or you solve, again, the system of equations. Now, so this is the kind of QM part. Now, a little bit about machine learning, right? I think at this age, it's a lot of hype, right? So it's important to kind of set language straight, right? So this overall field of AI, which is very broad field, that essentially technique to mimic human behavior and activity, right? So this very broad. Now, inside that field, we have methods of machine learning that use statistical techniques, statistical methods, essentially that finding the models that improve their performance with experience. Experience usually data, and improvement is typically geometric. Now, the deep learning and neural network is a subset of machine learning, where we specifically use one class of models, right? Inside the machine learning field, there are many types of machine learning models. Now, in the deep learning field, we use neural networks as one class of those models. It's more or less the same. Now, we live in this third age of AI, right? So this field started after World War II, kind of late 40s, early 50s. This is where some of the fundamental progress was made, perceptron. And then, as you can imagine, at the time, computers were very rudimentary, with little data. So we have this first AI winter. And then kind of 80s and 90s, this is where the fundamental algorithms, things like backpropagation and convolutional neural networks were discovered or invented. But again, computers were not there. So now we have kind of third age of deep learning explosion, where you see all those cool systems, AlphaGo, AlphaFold, all these self-driving cars. So the question is, will we have enough data and algorithms to deliver this time when it's going to be next winter? So, fundamentally, neural networks inspired by how our brain works. But again, this is the neuron inside the brain. Our brain has hundreds of billions of neurons. So you have, this dendrites, axon, and the actually the message inside the neuron transmitted through a lot, very complicated biochemical process. There is a bunch of proteins mediated by shuffling different ions and molecules. So this is biological neuron. Now the neural network was inspired by that. That's actually, for your kind of curiosity, these are two neurons inside the brain. You see this is axons, connections, and when the activation comes, you see how complex the connectivity inside these two neurons. This is the brain of a fruit fly and kind of the patterns of activation. You see how complex connectivity and interline between the neurons are. And therefore, neural networks are very simple mathematical approximation to how brain works. And this is biological neuron, this is a mathematical neuron. In the simplest term, right? So perceptron would be a binary output neuron that sums weights that in common. Here is a little function, and as soon as the sum of the weights go above certain thresholds, neuron activates and outputs 1, otherwise it's 0. Now you stack them in layer, and you see how simple connectivity is. And again, when somebody say, oh, neural network, this is how our brain works, right? So in fact, neural networks are very, very, just inspiring. And therefore, artificial neural networks are, one of the set of machine learning algorithms, very simple parametric model, how our brain works. Now, we use neurons as a basic process unit of neural networks. And this activation function is typically a very simple nonlinear function. So neurons pass store information, or can pass this information, or there are lots of different architectures that were designed to solve specific tasks. And the beauty of them is the scale to massive data. Some of other models, we're limited by how much data you can squeeze it in, but here it's unlimited. You see the Facebook, OpenAI, all these companies use billions of data points to train. Now, little bit anatomy, right? So we have how neural network works. So we have our X typically denote the input data, Y, our output, and this circle is typically neuron. So this is input, neuron, output. If you try to open this neuron, we have two things. One, we have affine transformations, typically linear transformation of your input through a set of weights. Gives you this hidden state H, and then you pass it through activation functions, non-linear usually. Now, and then you stack to it, right? So if you have two-dimensional input data, you learn two sets of weights that go to the Y, and essentially you can expand it every neuron, so each connection, each line here, will have a little set of weights, plus a bias. So they have this W11, W12, and W10. Same for the second neuron, and then you pass two hidden states to some kind of output function to get you one, right? So this is our output function, and then you define your loss. This is the things what you care, kind of a metric, and you see the prediction, how bad it is, or how good it is. You define the loss, and the way how neural network trained through backpropagation, so you apply chain rules, and you tune the weights, those W, with respect to minimize your loss, right? So calculus, right? So loss function. You can stack these things, right? So you can have a couple of hidden layers. So this is the first layer called hidden layer 1, layer 2. You can have arbitrary number of layers. You can also have different number of neurons. For example, there's 3 neurons, and overall you have the full flexibility. How many neurons you have, how many layers you have. Again, neurons can have different types, and hence we have this idea that you do architecture design these problems. Now, numbers of input, dimensionality of input depends on your data, dimensionality of output depends on your problem. On a computer, that's typically how a neural network looks like in Python. Now, in this kind of field-forward type of neural networks, not very good for certain things. So, for example, if you want to do, a detector of cats, right? Most of the videos and images are cats. Now, imagine if you have a cat here, right? So this set of weights would activate. This is the red set of weights, right? Activate. If you move your image, what would happen? Now the green set of weights need to activate, which means you need to parameterize this cat detector at every position, and this is not very good. Which means that our feed-forward architecture is not invariant to the position of the cat, to the rotation of the cat, right? And this is very important, especially for molecules, because if you translate a molecule, rotate a molecule, nothing happens, right? Because of the fundamental physics. Like energy of the molecule is the same, molecules stay the same. So therefore, a lot of things what I will talk about is how machine learning algorithms adapted to domain-specific applications, and the image detection is the first one. And the fundamental things that images are local, because if I take this block here of images, right? So when you hit the clouds, the pixel in the cloud or a part of the sky highly correlated. They have the same, maybe the same color. And also, objects are hierarchical, as molecules are. If I obscure this piece of image and ask you to fill it, say, oh yeah, sure, this is very easy, right? So this is a sunflower, I can add petals here, I can part of the leaf here, right? Because you know the local structure and all the objects are hierarchical, you can easily fill it in, right? Therefore, when we design neural network architecture, we want to learn this locality and hierarchy. And that objects are actually built from the smaller objects. And therefore, again, image is invariant. If I skew, rotate, you still detect, oh, this is still sunflower, right? So all of these things need to be encoded into the neural network. And hence idea of convolutional neural networks, which essentially learn this convolution operation, which is the matrix. Here is the example 3x3 matrix operating on the pixel of the image, and then you slide it along the image. There's a little video which essentially applies 3x3 matrix operation and producing the outputs. Now, sliding aspect takes care of the moving cat image, right? And hence the convolution operation was specifically designed for images. There's a step-by-step numbers. And before, a lot of people who work in the image processing were designing this kind of convolution operation, for example, as edge detection or sharpen. So if you open a Photoshop and apply sharpen operation, it used to be very simple, essentially matrix operation on your pixel of your image. Now it's getting a little bit more elaborate, but scientists used to design this operation by hand. But neural network essentially learns this convolution operator by through the matrix. And then you essentially take this convolutional layer, stack on them. So this is an example of very simple convolutional neural network. Inside, actually, this kind of very simple neural networks still used by the post office and some of the banks when you scan and recognize the zip code and the numbers on the check. When you submit it, essentially very simple operator, architecture, recognize numbers and letters. Now, a lot of problems what we do, what's called the supervised machine learning regime, right? So our neural network would be this magic function f that connects molecular features with some useful outputs, and then we collect historical data, pairs of molecules and useful properties. So for example, three-dimensional structure of the molecule, energy, or materials and the properties, superconductivity, temperature, or band gap, right? So those are pairs of what's called label examples. We use this as the training data, essentially find and estimate this function, minimizing prediction error on this training set, but then we want to apply it to something more useful, to prospective discovery of new molecules. And therefore, for example, you can use this function, for example, do solvent selection if you do reaction. Or a lot of drug discovery, you want to find these functions that connect molecular structure with binding affinity, how strongly the molecule interacts with this particular protein. Again, design a new catalyst, things like that, right? So hence, now we know with the supervised learning, with the neural network, how this all connected to Schrödinger equation, right? Again, this is our time independent Schrödinger equation. What we're looking at is to find the energy. How we do it? It's our supervised regression problem. So my ground state energy would be this magic function f from molecular coordinates. And this is exactly what's been what us and many other people are doing. We take neural networks, we put molecules in, we get energy. Also the beauty of neural networks, they're fully differentiable. So we can backpropagate, compute derivatives. And now we have forces. So we can do geometry minimization, we can do molecular dynamics. Now we can backpropagate twice and have second derivatives. Now we have a matrix of Hessian. And then we can predict other quantities and properties. And therefore, where all this comes together, right? If you look for the ladder of different computational scaling of different methods versus accuracy, as I told you before, if you're interested in simulating large system, you're kind of stuck in the realm of the force fields, that because simple analytical form are usually linear, or you have to, make investment and use more expensive calculations. A lot of you who work in materials probably use density functional theory, DFT here, which is in canonical form cubic, so it's scaled cubically with the number of electrons in your system. It's not that force fields are bad, but usually the transferability of forces, force fields is not very good, and therefore you have this very large uncertainty. And only paying the price is doing more expensive methods, you can reduce this uncertainty. In my realm of organic molecules, what's called the coupled cluster theory is actually called the gold standard, because it gives you an accuracy better than 1 kilo per mole from very high accuracy experiment. But the price to pay 7 order of scaling. So you can only calculate very few things. And of course, there is an unachievable heaven of full CI complete basis set, but this is sadly not practical. So what all of us are doing, we pick a reference method, again, often density functional theory, and we train this machine learning model that would approximate essentially Schrödinger equation or DFT equation at this level of theory. And we combine the linear scaling of neural networks with hope to achieve the accuracy closer to our reference data. This is the benefit of that. Now, but also, interestingly, this question goes a little bit more philosophical. Can a computer learn chemistry? And a lot of chemists were actually fascinated for a long time, right? Given the structure of the molecule, right? Is it toxic? Can I predict various properties of it? And so forth. So let me pause here and get to a quick question. Can you think about what might be the first data science application in chemistry? This is very well-known event, so hopefully, any guesses? What can be considered as the first data science application in chemistry? Any guesses?
Making a periodic table.
Exactly. Great. Periodic table, right? So what periodic table essentially did, right? You arrange elements in 2 dimensions, and where the chemical properties of elements gradually vary. And at that time, there were empty boxes where elements were not discovered, right? And then you can predict and infer the properties of certain elements because you know the neighbors. And all of that can be kind of combined, and what's important specifically for molecules, materials, how to represent the structure. Now, again, as a quantum object, molecule, when it's viewed by the molecule by another molecule, they're governed by these forces of fundamental interaction. So this is an example of electrostatic potential, the positive, negative parts of the molecule. Now, we, as a chemist, usually do sketches of 2D drawing of the molecule. But for the purpose of learning on a computer, molecules can be represented as the graph. So you have set of edges, vertices and edges. So the vertex would be atom, and the edges would be a chemical bond. This graph can be two-dimensional or high-dimensional, but you take this molecular graph, you can encode this connectivity, so types of the atoms, edges would be essentially a table of chemical bonds and type of chemical bonds. And from this chemical graph, essentially, you can use this graph structure for downstream machine learning tasks. And this is exactly how modern type of neural networks, specifically graph neural networks, are being designed. So you use molecular graph to do the operation inside the neural networks. Now, how it's connected. So you can think about when we learn this convolutional operation, it's essentially ordered graph on the grid, right? You have the central pixel, and each pixel will always have 8 neighbors, right? Because the image is square, ordered grid of pixels. So each pixels would interact with all neighbors, and you have the weights that's associated with the every neighbor. Now, what the graph can do is we go from the grid, off the grid. Now, our topology or connectivity now essentially depends on the chemical graph, right? So if I'm carbon, my valence is 4, I might have 4 neighbors, or I might have 2 neighbors, right? So now we have not regular grid, but the topology of the molecule would dictate number of these operations. So for example, this node have 4 neighbors, this node has 2, and then different numbers of the neighbors would essentially contribute to the separations. And therefore, modern type of neural networks for molecular material typically graph or a point cloud, which means in 3D, operation on the essentially atoms inside the molecular materials. And there is a zoo of these methods, right? It's absolutely impossible to talk. In my lab, we developed a couple of those. And so for the next few minutes, I'll talk about that. And when you think about this, you essentially design neural network by making the pieces of Lego blocks, stack them into layers, and essentially build in the architecture. So one of the probably most used neural network for organic molecules called ANI neural network. If you're interested, this is the reference. This was the first example, what's called a transferable neural network. We parameterize it. We release the pre-trained model, which you can plug into your favorite simulation package. It's been parameterized for kind of standard organic CHNO chemistry, and it gives you accuracy about 1 to 2 kcal per mole from our choice of DFT reference method, and speed up about 6 orders of magnitude. So instead of running on a supercomputer, you can do the simulation on a lab. So how it works? It's again work because we have what's called the near-sightedness principle, right? You've seen, all of you probably seen plots like that, right? This hydrogen molecule, water dimer. You can truncate interaction at certain cutoff. This is exactly what we do. We can truncate molecular graph. So for every atom, we find the cutoff. In our case, it was about 5 angstrom. We make this cutoff, And we built our little graph convolution operation just on this neighborhood for every atom inside the molecule. And essentially, your neural network zoom in one environment at a time. And your total energy of the system would be sum of these little atomic neighborhoods. Very simple. And hence, this is speed up, because we use only operation on the small part of the molecule. And so this is ANI architecture. You feed in your molecular coordinates. We do this operation, what we call the symmetry function, which encodes this atomic neighborhood, pass it through little neural network, compute this local energy, sum them up, and produce the total energy. Simpler idea, simpler architecture. Code is freely available on GitHub, if you're interested. We use PyTorch, hence the name of the torch ANI, so PyTorch ecosystem. If you're interested, it parameterized for kind of biogenic elements, CHNO, sulfur, and halogens. For computational chemists, we use 2 different levels of theory. You can do pretty much standard type of simulation, what you will see in the afternoon. Minimization of geometries, molecular dynamics, thermochemistry, things like that. Again, runs on a GPU. Essentially, it allows to do very accurate calculation, tensor energy surface of small organic molecules, gas phase reaction, thermochemistry, things like that. We also build packages for non-experts, right? If you don't want to code, so after 3D is a package, if you supply 2D structure of the molecule, a lot of databases would use what's called a SMILE string. So it's a kind of semi-human readable notation of 2D molecular structure. The problem is that it's 2D, right? And for calculation, you need 3D. So after 3D package, essentially helps you to find what is the most stable tautomeric state of the molecules, can find stereoisomers, and therefore after-made calculation of 3-dimensional structure of the molecules. Again, use a Python library or just command line applications. So how it works? What you can do, what we did these little applications, we go to database of SMILEs that have reaction of tautomerization. So, for example, like keto-enol, right, where the proton jumps. A little exercise, right? You can do it traditional ways with density functional theory. This is here on the y-axis versus, essentially this ANI calculation with ANI. In our case, we use what's called harmonic approximation to a free energy. So we have the electronic energy, zero-point energy, thermal correction, and entropy term. Compute the free energy of these reactions. And you can see with the wide range of the reaction energies, you have very appreciable R square and error of 1.5 kcal/mole. Again, run the simulation. The 80 calculations probably takes like 10 minutes on a laptop versus probably days on the supercomputers. Again, if you're interested, shameless plug, use Python pip install after 3D will do it. Or it's outside. Now, colleagues of mine, Justin Smith, who used to work at Los Alamos National Lab, used the same architecture and train ANI neural network for materials. So, for example, this is his paper to do shock wave simulation of aluminum. And you train this neural network potential, and then you can do fun simulation, like see what's the shock wave propagation, what kind of chemistry happens, nucleation of different phases, and study. So it's not the framework is generic, right? So we've done parameterization for the organic molecules, again extended for can be extended for materials. Since he works for the Department of Energy, there is also more interesting applications into F elements. Now, we work together to extend this model for chemical reactions. This very fresh paper that we published in Nature Chemistry to parameterize reactive potentials in the condensed phase. At this point, again, we talk about CHML chemistry. Again, if you're interested, pre-trained molecule in the GitHub. What we took idea and we inspired with the idea of nanoreactor. There's a seminal paper about 10 years ago that used ab initio molecular dynamics that cooks molecules in high temperature and at density. But it used ab initio, essentially DFT-based molecular dynamics, which is super expensive. Now we took this idea and we trained ML potential by cooking molecules and run this DFT calculations. This idea is that can we make this reactive potential transferable? And used to be, if ab initio MD is not an option, you have to parameterize empirical reactive potential. So for example, things like ReactFF is popular. And then we applied in a couple of different applications, formation, different phases of the graphene, combustion, things like that. So what you can do is, for example, you can study different phases of the carbon. So what is known experimentally and through the calculation, if you pack high density carbon at high temperature, run high temperature MD, what would happen? It essentially nucleates and forms diamond. In middle density, it gets kind of graphite layers. And at low density, you get kind of fully ring graphene kind of onion-like structures. And therefore, again, the neural net potential was able to capture that physics. We had lots of fun doing kind of combustion simulation. This example of methane combustion. You can study kinetic C, consumption of the oxygen, formation of various oxidation products, things like that. And kind of as an original nanoreactor paper, you can study prebiotic chemistry. For example, we've done this simulation starting from these prebiotic molecules and the formation of glycine. So you can see type of reaction network as it leads to the formation of the glycine. Now, again, 2017, ANI architecture. There are a lot of missing pieces, right? First of all, we did this truncation, which means it's ignoring a lot of long-range interactions. Fast forward, in 2019, our next architecture called AIMNet, idea from atoms and molecules. So now, to restore this truncation of long-range interaction, we introduced what's called the message passing. Also, we did many other technical improvement in the architecture. And the only what was missing there is we just encode just geometrical feature of the molecule. There's no way to put charge or spin multiplicity. And just last year, we have the AIMNet2, the second generation of AIMNet, which essentially extended the ability of geometrical descriptor with essentially the molecular charge and a spin state. And now you can encode radicals, metal centers, if you care about high spin, low spin situations, and for essentially supplying the total molecular charge in a spin. Again, if you're interested in technical details, it's a good thing. Now, what it does, since we condition neural network on the total molecular charge or a spin, it's essentially doing charge or a spin redistribution inside the molecule. So this is an example, conjugated molecule. If you attach or detach electron from this molecule, right? The system is conjugated. This is what happens. You will see the strong localization of the electron or a hole along these molecules, and formation what kind of a spin wave of phases, plus and minus phases. Now, if you use just geometrical descriptor and try to reduce that, neural network have no way getting this because it doesn't encode that. And this essentially this neural spin equilibration block allow us to do through this message passing mechanism allow us to describe that phenomenon. Now, with the second generation AIMNet, we again pre-trained and extended to 14 elements. So all non-metals. Again, you can work in charge and neutral molecules. Again, all the weights are there. It's a linear scaling in the kind of regime of a large system. So, for example, I can squeeze 100,000 molecules on a single GPU, and it's a fraction of a second to do evaluation of energy and forces. It's slower than a traditional force fields, but it's much, much faster than a DFT. And again, with the parallel tools, we can literally optimize hundreds of different conformers for small organic molecules for a few seconds. Now, again, and we see now as the AIMNet2 essentially as a foundation model, right? It's been trained on a lot of different quantum mechanical data, and now you can specialize them on different tasks, right? You can extend it for biological system. I'll show you a little bit about the reactivity and generative model and other things. So as part of our NSF center, we're really interested to extend these technologies and help computational chemists address the problem. Can we find transition states faster? Because this is a real problem. If you have reactants and products, transition state, this is essentially the highest peak on the minimal energy pathway between reactants and products. So the height of the transition state would determine your kinetics, how fast and slow this process goes, right? So, and essentially, this is a special point when you in your matrix of second derivatives have one negative frequency that essentially goes in directions of the reactants and products. Now, this is an example how this works, right? So this is a particular chemical reaction. It's a click chemistry. We can find this reaction coordinate and find what's called the intrinsic reaction coordinate between reactants and products, right? So this is the x direction reaction coordinate, and this is the energy, right? This is your reactant, this is transition state, this is your product. So this red points, which you probably cannot see, this is the DFT calculations of the IRC, and the cyan, kind of light blue, this is the AIMNet, and you see essentially how accurate the transition state is, literally on top of that. And again, we tested that in different reactions. Now, we extended that also to metals. For example, one of the most useful reactions, which is called the palladium catalyzed cross-coupling reactions, used in the pharmaceutical and synthetic organic chemistry, and it's include, so palladium as a catalyst. So this is an example of accuracy of different steps of the reactions, and the DFT versus the ML optimized geometries. So this is the palladium center and different ligands. You can also explore rich chemistry of different types of ligands, single palladium, double palladium, palladium in different charge states as well. So with that in the last few minutes, let me switch gear a little bit. I show you how neural networks help with computational chemistry calculations. But I think this data-driven technology also revolutionizing experiments as well. Because now in this interesting moment where science is kind of a crossroad. On one hand, we see this increase of scale of data, not only in computations, but also in experiments. So you have high throughput everything, right? You have all those interesting methods, algorithms, and technologies. And science is more and more complex, right? We solved simple tasks. Now we have really hard tasks to solve. So that's kind of on the positive side. But also we have challenges, right? So some of the instrumentation is more and more expensive. Right? This cryo-EM or NMR machines cost $1 million a piece, right? So the limited access to this instrumentation. Sadly, science became less reproducible. You see all these papers about reproducibility crisis in many cases in cancer and social sciences, maybe even in physical science, right? And I think that really begs for democratization. can we have access to all these facilities, but more students in various colleges and institutions who may not necessarily afford those expensive machines. And CMU, kind of shameless plug, been really interested in science automation for a long time. So for example, this is a homemade high-throughput robotic system of a colleague of mine, Stefan Bernard, who is interested in hydrogen evolution and catalyst design. So they built in their lab, a high-throughput robotic system to study the chemistry. Now we have educational lab. This is little animation that's dedicated for education, and specifically we have a master's program in scientific automation, where chemists, biologists, engineers come and learn how to run this robot, do high-throughput experiments, build closed-loop systems, and again, fully dedicated to education. And our latest flagship lab called CMU Cloud Lab. Many of you know what is cloud computing is, right? So this is the model of remote computing available on demand. These days, everything in the cloud. Now, take this idea, and can we have remotely controlled scientific lab with the same model, right? So this is the CMU Cloud Lab, cloudlab.cmu.edu, if you're interested. It's a partnership with the CMU startup called Emerald Clouds. And they actually, as a company, do commercial offering and sell the services to pharma and biotech. But the university made an investment, and we have the lab using the same technology on our campus. And it's dedicated to education and doing cool science. So we have almost 200 instruments connected, software platform, database, and it's remotely controlled. Now, this is an example of the instruments. We can do batch chemistry, we can do flow chemistry, we can dispense liquids, powders, lots of analytical characterization. You can do separation, mass spectrometry, you can do bioassay, various spectroscopy, NMR, HPLC, mass spec, microscopy, crystallography. We can do biophysical assays if they finally doing the cell-based and bioreactors. So with that, if you can express your experiment as the code for these instruments we have, you can orchestrate very complex workflow. This is like a floor plan. You can say, dispense these reagents, mix them, do that and that. So the system compile it, and basically you can do your experiments, which allow us to fully protocolize the experiment, right? Because hopefully, if the experiment is reproducible, if you run the same code, you hopefully get the same answer. You can make this closed-loop system and connect active learning with the high-throughput experimentation. Because now it's a less dependence on us, mostly graduate students who do experiment in the lab, because a lot of these things done through robotics. Again, flexible experiment design, really cool things. So let me show you a quick example. This is HPLC, high performance liquid chromatography. Very frequently used for detection of molecules separation. You typically need the advanced degree to run it. This is what you need to do to run HPLC. You still need to know what you do. But in the piece of code, you specify what's my column type, what's my sample, buffer, and a couple of other things, and allows you to run these experiments, which is really cool. And now, for example, what my lab is doing, we built a bunch of different machine learning models to see, anomaly detection if the HPLC experiment run, prediction of the retention time and other things. So to kind of facilitate this closed loop system, design make takes analysis really is streamlined. Now, what was interesting, that a lot of chemists very reluctant even to learn programming language. But we live in the age of generative AI, ChatGPT. What really cool thing a colleague of mine, Gomez, in chemistry and chemistry, is doing. Now you can expose documentation of the Cloud Lab to your large language model. And essentially now you don't need even to write this piece of code. You just tell the thing, run HPLC with that buffer. So it's really mind-blowing, right? What we can do. So you expose essential large language model to the document and to the documentation connected with a planner. Just tell it in plain English, essentially type run that, and it internally outputs the same code, and you can run the system. It's really mind-blowing how things are changing. So in my lab, we also work with synthetic polymer planners. So what we try to do is to automate the system for making polymers with desired properties. And we do it from a slightly different perspective. We use what's called the reinforcement learning. If you've ever seen a system like AlphaGo that plays essentially a game of Go, moving checkers on the board, right? Imagine now we'll play the game of chemical lab, and instead of moving checkers, the RL agent can pick reagents, for example, different monomers that synthesize a polymer. So, for example, make an elastomer. But then we can characterize them, for example, the GPC or IR spectrum, and then the system can then decide which conditions of experiment 3D print from this elastomer, and then perform, for example, tensile strength tests. And what my colleagues are really interested, can we design a material with best toughness, which is compromise between strain and stress, and therefore you essentially make this closed-loop system and teach the RL agents how to make the best polymer system by maximizing toughness, and essentially it learns how to run chemical experiments. All these three steps matter. With that, I think kind of the future is really bright. So we have hopefully our friendly AI that I show you that can accelerate simulations, that can be connected with experiment, and I can, in my lab, but many other labs and the companies have this bold vision. Can we make this AI-driven design of molecules, materials, hopefully in real time, one day, and you can connect this AI system. Maybe that can, be your support hypothesis generation, output, execute high throughput experimentation, characterizations. You can essentially close this loop, automate, from automated science to discovery, and therefore help us to solve some of the problems in molecular material design. Thank you very much for your attention. If you're interested, this is a bunch of links for our methods, and we'll be happy to answer questions.
Yes, thank you. Excellent talk. Because you brought up reproducibility, what do you think about the fact that when we're using, for example, PyTorch models, even if we use the same dependencies, the same architecture, there's a little bit of a stochastic process behind it. Even if I'm on two different computers, I try to train networks. My networks may not behave exactly the same because there's a little bit of that under the hood stochasticity that's dependent on the time, all this other stuff. So in the sense that we're not really living in like an open source world where all these GPU architectures are totally open, how do we deal with that as scientists? Is this the problem? Like, are those the storm clouds on the horizon that we need to be concerned about?
It's a very good question. I wish I know the answer.
Yeah, me too.
It's indeed the problem. But for example, what we found out that if you use the latest generation of like 400 series GPUs, unless you specify a couple of flags, and it's a terrible decision for us as a scientist that NVIDIA made. It uses approximate matrix multiplications.
Yep.
And the results are so bad that your simulation crashes unless you specify those two flags, and then things get in as it's supposed to. We are kind of this interested, uncharted territory that because AI drives the design of the chips, the precision actually goes down. The latest chips have 4 bits precision. It's ridiculous how, for us, how bad this is. Any students? Oh,
Not a student, but. Maybe I'll.
Please.
Oleg, nice to see you. I think that the Cloud Lab is operational now, right?
yeah.
So my question is, I'm assuming that you don't want to just run one workflow at a time, because that would be very expensive. So you want to sort of run multiple workflows within your lab in the same way that we run multiple jobs on our computers. But this Cloud Lab is very heterogeneous, right? With our normal simple computers, we have all GPUs, but we have all CPUs. And even just mixing CPUs and GPUs is always a challenge with different memory, RAM, for example. Here you have lots of different little bits, which can run into issues with staging and transferring these workflows at the same time. So my question is twofold. One, what has been your experience with staging these workflows simultaneously? And two, are there components that become kind of barriers or bottlenecks? Exactly.
Yes.
And what's that your experience with that?
It's a great question. We learn as we essentially we build the plane as we fly it. The smart colleagues at Emerald Cloud are actually not reinventing the wheel, right? So there's a lot of HPC experience for essentially scheduling. HPC like a sword, right? This is indeed much more complicated. And we try to, the original decisions were kind of informed what kind of chemistry we have. So we want to have, for example, HPLC like super useful, we have like 5 of them. So you don't have a bottleneck. But as we build this workflow, we still don't know what is going to be the slow pace. I think right now the bottleneck is the dispensing of powders, which is super slow. And other things that complicated maintenance of certain instruments, right? But indeed, it's going to be a very interesting challenge how from heterogeneous HPC to super heterogeneous lab. This is going to be very, very interesting, which we don't know answer yet. But the good thing, because for digital, everything is in database, we know essentially all the provenance, all the historical time stamps of the experiment. So hopefully to inform, I don't know, Cloud Lab 2.0, next design.
I mean, presumably there's a combination of residence time in the instrument as well as the number of calls to the given instrument.
And time to deliver samples or reagent or a solvent. So there's a lot of complexity.
So how extensible is Cloud Lab? Like, can you in a given every 6 months, can you start to refresh or add pieces, or is it going to be every 2 years or every 3 years? What's the refresh rate?
I wish I know that. I don't know, but it's super interesting to learn. We'll see as we literally just started.
This is sort of maybe a systemic question, but these generally, artificial intelligence and machine learning models, there's always questions about ability to generalize completely out of sample. And obviously this model is pretty powerful, but you said that to be really accurate for a specific use case, you have to sort of specialize and fine-tune it with training examples. Presumably those training examples come from actually running DFT or the like. And so, maybe this is a bit of a skeptic perspective on it, but is this not function, because we already have to do the DFT, the really computationally intensive work, in order to be able to tell whether we can use this model, is it not really functioning as a really elaborate lookup table for things that we have computed? And if it is there space between DFT and machine learning for sort of getting DFT, in an abstract sense, DFT result primitives and finding fancy ways of combining them so that we don't have to run the DFT from scratch every single time?
Oh, that's a very good question. And we have to be skeptical, right? So those things kind of sadly live in the AI hype. Well, it's sad. It depends how you think about it, right? But this is not magic. We teach class, at CMU, literally show how LLM and all this system works. This is not magic there. And there's no magic here, right? If you never see as, certain things, if the neural network never seen a collider, it will not. But again, chemistry kind of semi-local, at least organic chemistry, right? So it's not metal, right? So it doesn't extend. And essentially, if you see enough example to kind of capture the locality of the specific chemistry, then what we see, it works for larger systems. Right? So what you pay the price may be smaller DFT calculations, but then you apply them for realistic larger system. And so things like screening of large number of materials or reactions. This is where the benefit. Yes, you have to make the investment. And sometimes this investment can be substantial. But the payoff that if you sure, and there are ways and methods how to ensure that it's accurate enough. So then it will work. Right? I don't know answer your question. But you have to be careful, indeed you have to be very careful to am I getting the right answer for the right reason?
I'm the new to all this, so kind of going back to you talked about the computational neural network and with like human confirmation for observations. It's like a bit of a silly question, but do you sometimes have to account for like human error for some of these observations, or is it pretty like obvious for what you do?
You mean human error in terms of like data?
Just because I think on one of your slides you mentioned that like sometimes you'll train a model by like having a person select whether or not a certain observation is there. Or maybe I was misinterpreting one of your slides.
You mean in the example on the cats and
Yeah, like sunflower thing. Like
yeah. So yes, if your data set mislabeled, all those errors would be baked in. And there are examples from the images where it was. This is a very famous example for horses. So there's a particular neural network that was trained to recognize different types of horses. And what's happened is that all the horse data set come from the same photo agency. And the recognition of horses were not because it recognized the horse, but it was like a copyright stamp on every image. A neural network was very good in finding the stamp. I'll say this is a horse. So those kind of things are, this anecdotal example, but yeah, if it's mislabeled, then it's all propagated.
We're training it with capture, right?
Yeah.
Yeah, we're giving our services
Yeah.
for free, yeah.
So I have a question. So you were talking about this cloud-based lab, which sounds amazing. I mean, it's really cool. But you sort of threw in there that people are always talking about this, like ChatGPT can like write code and stuff. And I personally like to think that we're not at the point where ChatGPT can replace people who code. And also, my boss is here, so I'm going to say that I don't use ChatGPT other than to say that it sometimes works. But my question is, how extensively has that been used? Because it will make mistakes very confidently, like pretty frequently.
Absolutely,
I'm wondering,
yes.
have people used this and gotten results that don't work because ChatGPT lied to them about what the lab was doing?
Yeah, this literally is. I don't know answer yet, right? So. But what I want to think that we do have people at this point who basically very close to hardware to actually experiment. And when we run the experiments, we do the checks. There are certain checks in the back end. Like you cannot dispense a liter into the 10 liter pot, right? So there's certain things that are there. But the idea is that as soon as you protocolize the basic steps, then you don't need to write much more code than this is my new reagent, this is my solvent, and then connect to HPLC protocol and MR protocol, right? So you might not necessarily have to write that much code. So that is kind of, so you have people in place, there's certain safety checks. But indeed, I really don't envision that, you talk to a ChatGPT bot and, do things. So at least that intermediate future when you at least can, have the building blocks of the protocols. Like if you've seen how biology, modern biology works, right? There's a lot of protocols. I think with chemistry, material science, chemistry really lacks on that, right? Because a lot of things is like super custom, essentially a cooking book of recipes. Probably get in trouble with mine. Yes.
I feel like hypothetically, I don't actually do this. The use of ChatGPT, at least how I do it, like for example, I'll just use math homework, is if I'm completely lost on something, I use it as like an information gatherer rather than anything else and use my own human brain to discern things. Is that what you're getting at?
Oh, sure. What's really good, like just probably a few weeks ago, a colleague of mine wrote very complex function in PyTorch. So done some operation. And we play the game. So I put this function to ChatGPT and say, hey, what it's doing. It was very good. It was explaining that. And even more, you can ask to annotate your code and write the computation. It's unbelievable how good those systems are. Especially if you can expose more than one function. So I think very quickly, ChatGPT will not replace, but it's going to be your, it's like 10 years ago, very few people had a cell phones, right? Now this is part of us. If this is lost, my life is done, right? So maybe in a few years, so this assistance would really help us to do certain things.
Thank you for the talk. So I guess I have a technical question about the AIMNet2. So how can you guarantee the chemical loads? So how do you get the chemical loads inside your network? I noticed you have a function of this in the input instead. How you embed the chemical loads inside these?
Can you speak up a little bit? Sorry.
Yeah. So you have the AIMNet2.
Yes.
How can, because it's a black box approach. I guess, so how do you guarantee the chemical loads inside these?
Oh, the chemical rules. Sadly, we can't guarantee certain things. There are certain symmetries and invariances inside the neural network, right? So you rotate molecule, you translate, and it just stays the same. A few other things. The total molecular charge or a spin is conserved, right? So there are certain things. But in principle, you can put 6 carbons, make it 6 coordinated thing. It's nonsensical. Neural network will give you an answer. To certain things, there is no safety checks for that, right? And at this point, it's more on the user informed responsibility, right? Because again, it's student-driven code, maybe not types of errors, but catch. We can catch certain things when 2 atoms on top of each other, right? That gives you an exception, right? But there's nothing that prevents you to do random blobs of atoms, shove it in, and it gives you a number. The question is how realistic this number would be. So again, to that sense, there are certain things we cannot ensure because it's black box.
Yeah, I guess a follow-up on the kind of cloud labs discussion we've been having here. The way you've described it so far, it seems very kind of like a script oriented. You do this and then this and then this. Though it seems to me like the main draw of being able to automate these kinds of processes would be to do like a bunch of different operations in parallel and see how the peaks of an X-ray spectra, continuous vary with composition of your precipitate or whatever you're doing. I guess my question is about how modular these analysis and experimental methods are, and whether you can incorporate them into a more, I guess, comprehensive system, rather than just link them together operationally, right?
You can run. So I see the things where this technology is useful. When you do often the same things, you run a reaction, you want to optimize. You run synthesis, and you want to explore. You have zillion knobs in your experiment, and you want to achieve certain goal. I think this lab will not help you if you want to hack instrument, do some interesting stuff that violates your manufacturer warranty, what my colleagues often do. So this is specifically designed to repetitive tasks. However, the question of modularity is the instrument is available, you can just run it for wherever, if all the knobs been exposed as the option to the function, you can vary certain things, right? Buffer, solvents, temperatures, right? Then you can adapt to whatever your application demands. And in that sense, you can just use one instrument. You don't need to, use complicated workflow. But I think the beauty is that each instrument has a Lego block, right? And you can stack them up as little or as many blocks as you want. Are we doing on time?
No, it was a good discussion. I have one last question for you while we have you on the spot. So we have a lot of students here. I think some of them might be 5-10 years out from maybe entering this field. What's your opinion about where the frontier is for them to have a vision about how they can contribute to this?
I wish I know the answer. So when I was doing PhD in computational chemistry, quite a few years ago, it was before ML, and that field was obscure, kind of stagnant, because nothing happened. I think we live in very interesting times. I don't know where we end up, but we have this interesting technologies, hardware, software, that allow unbelievable creativity, right? Yes, there's a hype of ML and AI, but there's so many things, especially in science, that are done very custom, non-scalable, kind of artisanal way, right? And maybe, think out of the typical box how, your PIs or advisor done stuff for 20 years, right? And come with these crazy ideas. And hopefully, very cool things will happen.
Thank you very much.